The first thing we're asked to do here is find the relationship between h and r, the height and the radius of the water inside this cone. And that's really helpful to answer questions like part B. We need to find the rate of change of the radius or the height. So if we look over here at this, we have a container and then the water inside the container. And the container has a radius of 4 feet and a height of 10. So the container has a radius of 4 feet and a height of 10 feet. We can talk about the relationship between those two values and compare them to the water height and radius. So the water is inside the container, but the radius and the height are not always the same as the container unless the container is totally full. So after it starts draining, we have some radius r and some height h. We can construct this relationship because there are similar triangles that exist here. They both share an angle here at the vertex of the cone. They're both right angles between the height of the cone and the radius, and then they have the same angle here between the radius and the edge of the cone. So those two triangles here, one little one for the water and a bigger one here for the cone or the container, are similar triangles because the angle measures are the same. Therefore, the ratios between their similar sides must be the same. The water is contained in the container, so that sort of should make sense to you. From there, we can make an equation or a relationship for radius compared to height. Simplify the 4 feet over 10 feet, we get 2 over 5 as the ratio between the radius and the height. Or even further, we could solve this equation for what the radius is in terms of the height. The radius is 2/5 the height. That'll help us in the next part of the question to find how fast the water level is dropping from the cone so that we can reduce a variable. I'll show you that now. First thing you notice is that the water is draining from the cone at a rate of 5 cubic feet per minute. That's already labeled for us there. We also know that the volume of the cone is 1/3 pi r squared h. So we have an equation that relates this guy, the exit rate, which is a change in volume with respect to time, to the radius and the height. The problem is that with the water in there, the radius and the height are both changing. They're both variables. They both will have a rate of change with respect to time. So if we try to execute the problem like this, now we have two variables, r and h. That's why this equation is very handy. Using that fact, for r equals 2/5 the height, we can simplify this equation or eliminate a variable. So let's substitute 2/5 h right here for r. That makes the equation for volume only in terms of one variable, h. 1/3 pi r is squared times h, and r is 2/5 of h. So by cleaning that up, you find that the volume is 2 squared is 4 over 75, 3 times 25, times pi, times h cubed. There were two h's there, h got squared times another h. That's an equation, remember that's step 2, that relates the variables. Once we have an equation that relates the desired variables, of which there are 2, right? The volume is changing and so is the height. Then we can differentiate the equation in step 4 to talk about the rates and how they're related. So we want to take the derivative with respect to time of this volume equation. The variable is h. He's the only thing that needs to get differentiated. So we see that the change in volume with respect to time is 4 over 75 times pi times the derivative of h cubed, which is 3h squared dh dt. Then from here we can identify that the thing we're talking and we're finding is how fast the water level is dropping. We want to know what dh dt is. So there's the variable we want to solve for. We also know that h is 6. So, excuse me, I think I said step 3, but maybe I said step 4. This guy was step 3, take the derivative. Step 4, evaluate this equation at h equals 6 feet. We already know the change in volume with respect to time is a loss of 5 cubic feet per minute. Pi is pi, 3 is 3, h is 6, so we find dh dt to be the change in volume with respect to time times, let's simplify this a little bit, 75 divided by 3 is 25. But then we'll flip that over to get it to the other side, so 25 over 4 pi times, this guy was 36, so 1 over 36 for the h squared, where the dv dt is 5 cubic feet per minute. So this is negative 5 cubic feet per minute times 25 over 4 pi. Those are all just constants times 1 over 36. Remember, that's feet squared from h squared. Gives us a change in height with respect to time of about negative 0.276 feet per minute. So these cone problems, this is really the key right here, is just finding out how to simplify the equation in terms of R and H. Use similar triangles.